product of two spherical tensors, we look at how the product transforms under rotation. So like what we have here. So we rotate product tensors, and then we insert just a unit operator here in between the two spherical tensors, and we use the definition of spherical tensor. So when it is rotated, it will be some linear combination of the other components of the spherical tensors with its coefficients, which are the matrix representation of the rotation operator. So then we see immediately that the product tensors then transforms according to the direct product representations. So if we compare this with the product of two angular momentum states, that is exactly what we have. Yes. So if we rotate a product of two angular momentum states, then it will transforms according to the direct product representations. So this means that decomposing a product of the spherical tensors into its irreducible components is really identical to decomposing a product of two angular momentum states into linear combinations of total angular momentum eigenstates. So let's write this down more clearly. So what I want to say is that we have a product of two angular momentum states. Then we can, of course, always introduce the completeness relations like this. So this is just the inverse of the Clebsch-Golden coefficients. So then that gives us the decomposition formula for decomposing or for expressing the product of two angular momentum states into well-defined total angular momentum states labeled by this capital J and capital M. Yes. And of course, we have the reverse relation. We can also write it like this. So that is just a unit operator, and we just put GM here. So these are just the Clebsch-Golden coefficients. So then we look back at what we have here. We compare with this one here. And then we can immediately deduce that the corresponding quantity for the tensor operators would be this one here. This will be sum over Q1, Q2, say. So a lot of indices here. And we have the Clebsch-Golden coefficients. So So this is just the analog of this one here. It's identical. So this is the analog of product of two angular momentum states, and we have the same Clebsch-Gordan coefficients that determines the linear combinations. And we also have the reverse. Let me erase this. So we have the reverse equation. So then we have K1, Q1, K2, Q2. So we can see that this must be equal to sum over Gm. So these are operators. So this is just the analog of this one. So you see them, they have the same structure. So in the notes, I worked out explicitly this results here using the decomposition formula. So if you have the, let's say, Q1 cos Q2, so that is the direct product representation, then you know that this can be composed into the reducible components using the Clebsch-Gordan coefficients. We have talked about this when we discussed the addition of angular momentum. So it's exactly the same algebra, the same structure. But let's check that this object here, that is Tm, does indeed rotate or transforms according to the irreducible representation J. So let's check that this is equal to this one here. Like that. So that is the analog of this. Okay. So let's do that. Let's see, I can write this down here. So we want to rotate this tensor operator. So then we use the definition of the Jm, and that is just equal to 2. K1 here. Like this. So then this becomes what you get, sum over K2. So takes a while to write this down, but let's do this properly. So now we can use the orthogonality of the Clebsch-Gordan coefficients. So then we sum over Q1 and Q2. That gives me J prime delta M double prime. So then we get what we want to show. Like that. Yes, so this object does indeed transforms under rotation according to the irreducible representation dj. So of course we also have to make sure that the j here runs from k1 plus k2 all the way down to k1 minus k2. Yes. That's the same as when we add two angular momentum states. It's the vector addition formula. Okay, so that is the general way of decomposing the spherical tensors into its irreducible components. This is basically what we have here. That one, and I think I've just written this down before that. That the corresponding, I call it Z instead of Q, doesn't matter. So that is just then the sum over Jm. So this is how it is decomposed. Yes, it is these two is just connected to each other. It's just you just used the orthogonality of the Clebsch-Gordan coefficients. So this is how the decomposition of the dyadic that we had in the beginning as an example was done. Yes, this is so in the case of K1 to K2 equal to 1, so that's the vector operators. Then the J here goes from 0, 1, and 2. That gives us then in total 9 components. So these are decomposed into the different J, and each J then is given by this expression here. So those coefficients, the expansion of the dyadic is given here by the Clebsch-Gordan coefficients, essentially. So the only thing we have to worry about is that in the case of the dyadic, we have simply multiply two vector operators in the Cartesian representation. So they have x, y, and z. But in the spherical tensor, you want to form this type of component instead. And the Vz is the same. And the Vz is not affected. So these are the spherical tensors. So but they are just equivalent, yes, to the Cartesian one in that case. It's just a linear combination of the Vx and Vy. Okay, so now we want to do the last part here, which is the Wigner-Eckart theorem. So the Wigner-Eckart theorem is a very important theorem which provides an expression or formula for the matrix elements of a spherical tensor operator between two angular momentum eigenstates. So we have tensor operators here, and we have two angular momentum eigenstates labeled by J prime M prime and Jm. And we can show that these matrix elements can be written as a product of the Clebsch-Gordon coefficients. So I just write Clebsch-Gordon coefficient. It means here more explicitly would be, and I use the full notation here. So I put the JK also, MQ, and we have JK, J prime, M prime, like this. So this is the Clebsch-Gordon coefficient. So this J prime on the left hand side here, or on the left state, must be one of the k plus j minus j. We'll show this. And in addition, we also have some constant. So it is written in a kind of funny way. So that is written like this, with double bar, and an operator we just label k like this, and then divide it by square root of 2j plus 1. So these are just a constant, so we don't need to worry about this notation, and this is just a notation, yes. And so it's basically just a constant which depends on alpha prime, j prime, and alpha and j and k, but does not depend on the mm prime and q. So this is the whole point, that these matrix elements can be written as a product of Clebsch-Gordon coefficients, which carries the dependence on the m prime, and q, and multiplied by a constant which is independent of the mm prime and q. So that is a kind of useful, because this constant is independent of mm prime and q. So this means that if we take a ratio between, let's say like this. So I want to say that if we take a ratio prime and another matrix elements with a different m, so let's call it m1, let's say, and a different q, so let's call it q prime, and m3, So like this. So this will be just a ratio of collapse coordinate coefficients. Yeah. So this means that since the collapse coordinate coefficients can be calculated independent of the system, so these are just properties of the geometry of the systems. So that can be calculated once and for all. You can look it up in some books, or you can write the code to calculate the collapse coordinate coefficients. So if I know one of these matrix elements, then it is possible to use this formula to compute the other matrix elements by taking this ratio. So that's one use of this Wigner-Ricard theorem. So what do we actually mean by this label alpha here? We can illustrate this by considering an explicit example. So we have state like this labeled by alpha. So we can think of about, let's say, an atomic problem, hydrogen, for example, and we look at this the position representation. So this is then just alpha j depends on the radial distance times the y. Well, not L here. I call it j. So let's use gm like that. Yep. So the alpha here, of course, corresponding to the principal quantum number, like in the atomic problem, and this j is just the L here. So this alpha carries the dynamics of the system. It gives information about the dynamics of the system, about the actual system. Whereas the geometry, that is to say the fact that the potential is spherically symmetric, is contained in this spherical harmonics, or in the GM. So this carries the dynamics. So by the dynamics, we mean the potential, say, of the system. So if I have two different spherically symmetric potentials, then it will give me different function, radial function, alpha j, or alpha j, yes, or RNL, yes. This tells us the dynamics, the actual system, yes, but not the symmetry. So the symmetry is carried in this spherical harmonics, or the JM. So this is what we mean by the label alpha. It's an example. Okay, so how do we understand this Wigner-Ricard theorem? So the Wigner-Ricard theorem can also be understood in terms of decomposition of the product representation into its irreducible components, just like when we form a product of two angular momentum states or a product of two spherical tensors. So if we look at how this state here transform under rotation, this state here. So forget for the moment the bra. So we just look at this state here. That's there. We rotate it. So this is a state. So we just apply the rotation operator. Then we can do the following. So we have dr, dk, q, and we can insert the unit operator as usual. So So that's the usual trick. And like that, so this is the same as this thing here. Then we see that this part then um, transforms according to this thing here. Let me, if I can continue here. So I have sum over q prime, k q prime, k here, q prime q. So I drop the r just to make it simple. So that one we know also. So that is just, so we multiply this by sum over m prime alpha j m prime dj m prime m, like this. So that is just the transformation of the angular momentum states under rotation. So we see that this object here transforms under rotation according to the direct product representation, because this is this thing here is just the product of these two. Yes. So that is just dk q times dj m prime m. So that's the definition of the direct product representation. So again, we see the same kind of thing. So this this state, which is a product of tensor operator and a state, angular momentum state, they transform under rotation according to the direct product representation, just like the product of two angular momentum states and the product of two spherical two spherical tensors. So then we can conclude. We can conclude that in the same way, like we did before, that this quantity here transforms under rotation according to the irreducible representation dj. Yes. So this implies that this object, this state here, must be then, or must be possible. It must be possible to write this as something which is proportional to this expression here. So we see that so we see that this thing here must be proportional to the state J. Yes. So let's do this in a more proper way. So what I want to say is that we have sum over qm q like this. So this is just the analog of of the total angular momentum state. So if we make a comparison here, so this will be so this should be QM here, not GM. And so these two are just the analog of each other, yes? So we know that this is equal to JM. So we say that this product of two angular momentum state is just the analog of the product of the spherical tensors and the angular momentum states, Jm. And this is just the Clebsch-Gordon coefficient. So that is also the Clebsch-Gordon coefficient. Then we can argue that this must be proportional to capital Jm. Yes. And the constant of proportionality will depend on alpha, k, and j. Yeah, like this. So we can use the orthogonality of the Clebsch-Gordon coefficient or the unitarity to get this. So we multiply both sides by this whole thing by GM QM like that. Oh, could be a different, should be a different label here. Let's say Q prime M prime and sum over JM. Then we have the orthogonality of the Clebsch-Gordon coefficient. So that will pick up Q equal to Q prime and M equal to M prime. So I just call it Q and M. Yes. So then this must be given by J sum over GM like this. Yes. So if we take the matrix elements or take the overlap of these with respect to some other state labeled by alpha prime and G prime and M prime, then we get the Wigner-Eckhart theorem. Okay, so we say that this J prime and M prime must be equal to this J, okay, M, yes, because otherwise it will be 0. So we'll pick up one of these terms on the right hand side here. So the J will be equal to the J will be equal to J prime, and capital M must be equal to M prime. Yes, and we have a possible constant of proportionality because we have this label alpha prime. Can also depend on J prime, like this. So this is the Wigner-Eckhart theorem. So this constant of proportionality is what is written as alpha prime j prime, and then double bar. That's one. So it's just a constant, yes. And it is just the Clebsch-Gordon coefficient. As we have seen, we can understand the Wigner-Eckhart theorem in terms of decomposition of a direct product representation into its irreducible components. Yes. So what we have here is that we have a spherical tensor labeled by K and Q. And then we have angular momentum states labeled by Jm. So the alpha here is not so relevant. What's more important here is the, the J and M label, because that tells us how the state transforms under rotations. So this product then transforms under rotation according to the direct product representations. So if we make a summary, see if we can get rid of this. Yes, so yeah, write a little summary here. So we have a product of momentum states labeled by M1, M2, and we have also considered a product of two spherical tensors, X and Z here, labeled by K1, Q1, and K2, Q2. And in the case of the Wigner-Eckhart theorem, we also have a product of the spherical tensor and angular momentum states. So all of these objects here, these three objects, they transform under rotation in the same way. So they transform according to this direct product representation. So what's important is not what the objects are, but rather how the object transforms under rotation. So in this way, we can understand the Wigner-Eckhart theorem by recognizing that this state here can be decomposed into the different total angular momentum states. It's just like what we have here. And then when we take the matrix elements with another angular momentum state, then that state must be one of the states in the decomposition of these products here. Yes. So we go back here. So when we take the matrix elements with another momentum state, then this is not zero, only if m prime is equal to q plus m. So that's a bit like in the addition of two angular momenta, the capital M, which is in this case equal to M prime, must be equal to Q plus M. And the J prime must be then one of the J in this decomposition. Yes, these are the decomposition formula. So then the J prime must be one of these. So this J here is limited to K plus J minus J. So it must be one of these. So the J prime must be one of these, capital J. Otherwise, the matrix elements will be 0. It's a very useful formula because instead of just blindly calculating the matrix elements and then discover that they're identically 0, we can analyze this before we do the calculations. Then we know that certain matrix elements are 0, so we don't need to calculate those matrix elements. Yes. So just to give an example, if k here is equal to 1, let's say, and j equal to I don't know, let's say 1, then we know that the only non-zero j that can contribute to the matrix elements will be j equal to 0, 1, and 2. So if we have an angular momentum states with j equal to 3, well, then we know in advance that this matrix element is going to be 0. So we don't even need to actually calculate them. Yes. So just from the symmetry, we know that it is 0. So this is, I think, the last part of the angular momentum chapter. Let me look at the time. Oh, it's almost 11. So, so maybe I can ask if you have questions up to here. Okay, so this is the key point is here. So the product of these x, whether they are angular momentum states or spherical tensors, they all transform according to the direct product representation under rotation. And then we can use the decomposition formula, or the sometimes called the Clebsch-Golden series. So that is basically just transforming the matrix into this block form. These are the block form, and this is the Clebsch-Golden coefficients. So the algebra is identical to the algebra of adding or forming the compound states in angular momentum. Okay, so you don't have questions, then we can have a break here. It's a good place to have a break. And we continue with symmetry in quantum mechanics after the break. So let's see. Okay, so we can meet again at 1:15. Okay, so I start with a new topic, symmetry in quantum mechanics. So very often we can take advantage of symmetry. So if a system with a certain Hamiltonian is invariant under certain symmetry operations, then we can make use of this symmetry. And there are also some important consequences associated with symmetry. So what do we mean when we say that an object is invariant with a symmetry operation? Well, this just means that the system or the object is indistinguishable before and after the operation. So in the case of Hamiltonian, this is what we are interested in quantum mechanics, then the Hamiltonian is invariant under the symmetry operation, let's say call it S, if that operator commutes with the Hamiltonian. So we'll discuss this a bit in more detail later. So just mention it here. And if the symmetry operation is continuous, like for example translation and rotation, so these are the two most common symmetry operation, then the symmetry operation can be written in this way here using a generator. So this is very much like what we had before with translation and rotation. So in the case of translation, this G is the generator, is just the momentum operator, whereas for the rotation, the G is the angular momentum operator. Yeah. So let's start with symmetry in the classical mechanics. So we use the Lagrangian formulations. We have Lagrangian here, which is a function of canonical coordinates, q at q prime. So that is kinetic energy minus the potential energy, like this. And then as usual, we have this equation of motion. Q prime is equal to Q, so that is just the momentum. Q dot like this. Okay. So these are just equivalent to Newton's law. But we can also work with a Hamiltonian, which is actually just Legendre transform to Lagrangian. So the momentum here, P, is the conjugate variable to Q prime. So P and Q dot are conjugate variables. So P is equal to dl dq dot, so dot here. So then we can do Legendre transform. If you forgotten about Legendre transform, I have it in the appendix. So that is then given by PQ dots, the product of the conjugate variables, minus this L. Yes, and that gives us the usual Hamiltonian squared upon 2m plus instead of minus VQ. So now our variables becomes Q and P instead of Q and Q dot. So this Legendre transform is quite common. You also have this in statistical mechanics, different functions. Some thermodynamic quantities depends on the pressure, volume, and temperature, and then you can Legendre transform for one of the variables, and then you have the thermodynamic quantities as a function of energy and volume and temperature, for example. So we have then the equation of motion, P dot equal to minus dH dq, and Q dot here is become dH dP, conjugate variables. That is equivalent to the Newton's equation, of course. But suppose now that this Hamiltonian or the Lagrangian is invariant under displacement, under, for example, translation or displacement. So this implies that dH dq must be equal to 0 because it doesn't make any, because because the Hamiltonian is invariant under translations. Then dH dq is equal to 0. So that would also then mean that the P dot is equal to 0. So this implies that the P is a constant of the motion. Yes, P is a constant of motion. It's constant. Momentum is constant. So this is actually a rather general result. If the Hamiltonian possesses a symmetry, but a continuous symmetry, it is important that the symmetry must be continuous. Yes? Then there will be some conserved quantities. So the symmetry, such continuous symmetry here is important, that it is continuous, not discrete. Continuous symmetry usually imply conserved quantities. So in this example of the translational symmetry, then the conserved quantity is the momentum. Yes. So this is a general theorem due to Noether. I think that's correct. Noether, Noether. Yes. It's a remarkable woman. Yeah. This is the consequence of symmetry. So in quantum mechanics, actually there are two important consequences of symmetry. So first is this concept quantities. So now I'm talking about quantum mechanics here. So apart from conserved quantities, usually symmetry is also associated with degeneracy. So conserved quantities, like in the classical case, but it also usually implies, not always, but often it implies degeneracies. Symmetry often implies degeneracies. Okay, so these are just some general things. So let's do this more detail. So what do we mean by symmetry operation? So we have symmetry operation, let's call it S. So just to have something concrete in mind, so it could be translation and rotation, let's say. Those are the two common symmetry operations. This can be written, as we said before, in terms of generator, call it G. Can do this like this because it's continuous, so we have an infinitesimal operation. Yes. And G here is a Hermitian. Like momentum and angular momentum operator. So now we have, let's say that we have a state, arbitrary state, psi, and we perform a symmetry operation on this. So we look at the state, psi, put the S inside that. So I label with S. Then we say that if the corresponding Hamiltonian is invariant under the symmetry operations, then it means that the matrix or the expectation value of this Hamiltonian in the rotated state, psi s, is equal to expectation value of the Hamiltonian in the original state. So that's the definition of invariant. So this means invariant under S symmetry operation. I think it makes sense. Because the symmetry operation that rotates the Hilbert space, and rotates the states. So what is then the consequence of this? So this means that if we use this thing here, then we have psi s, and then we have psi dagger. We have s, psi, sorry, there shouldn't be any s here. It's difficult to, yeah. Let's go to that one. So that then, since the state is arbitrary, we have not specified that is, so that would imply that yes, like h s is equal to h, or since s dagger is unitary, it's also important to say that it's unitary. But then it implies that the h commutes with the symmetry operator, like we said in the beginning. So that's definition. We can take this as our definition of invariance, the Hamiltonian under symmetry operation. And if we use that expression, it would also imply that H commutes with G. That I think is quite clear. It's also 0. Then if we work in the Heisenberg picture, so we multiply this both sides by that one. that of course is equal to 0. That would mean that G in the Heisenberg picture commutes with a Hamiltonian. So this has an important consequence because this is just the Heisenberg equation of motion. So that would then tell us that dgh dt is equal to 0. So the gh is a constant of the motion. Constant of motion. So this is as we can say, it's a simplified form of Noether's theorem. So if the Hamiltonian is invariant under certain symmetry operations, then we have a conserved quantity, constant of motion. So one consequence of this is that since G commutes with H, then we can choose the eigenstate of the Hamiltonian to be the simultaneous eigenstate of G. And we can also show that if we have a state, let's call it phi, and that is an eigenstate of the generator, then the state remains an eigenstate as a function of time. So if we look at this as a function of time, so now we just apply our time developed operator. Let's say we start at time t 0, make it simple. So if we then apply the generator, this state, well, G and H commute, so I can just slide over, slides it. This since G and H commutes, but this is just G times phi. So then we see that it is equal to G T. So the state remains an eigenstate of the generator because of the fact that it commutes with a Hamiltonian. So that's one important consequences of this. So we said before that the second consequence of symmetry is the presence of degeneracies. So let's see how this comes about. So our starting point is that Hamiltonian commutes with a symmetry operator. So now let's say that we have some state n, call it, which is an eigenstate of H with eigenvalue En. That. So now if we apply this commutator onto this eigenstate n, well, that's of course 0 because 0, And if you open up this commutator, then we get h s like this minus h sh, and so that is equal to 0. So this thing is just En times the eigenstate, and so that then implies that h n is equal to En s n. Yes. So the rotated state, where the rotation is done by the symmetry equation, is also an eigenstate of the Hamiltonian with the same eigenenergy. So if this state is not the same as the original state, then we have degeneracy. So by not the same, we mean that not the same up to a constant, multiplicative constant, of course. So we see we have degeneracy. So we have more than one state with the same eigenvalues. So since we've been doing angular momentum, we can take Hamiltonian as an example, which is invariant under rotation. So let's say that H is invariant under rotation. So that would imply that the rotation operator is equal to 0. So for example, we have an atomic problem, like say hydrogen atom. The potential is spherically symmetric. More general problems, and you have spherically symmetric potential. Could be harmonic Slater potential in 3 dimension. So it is D, if we write it in terms of the generator, is given by 1 minus H1 J dot M like this. D phi there. So that's the operator, rotation operator. We write it in terms of the generator J. So then we know this already. So the J and the H commute, and we know we have this J squared, which commutes with H. So this implies also that dj Heisenberg dt equal to 0. Yes. From the general theorem that we had before. So that implies that the angular momentum is conserved. Conservation of angular momentum, because the J is angular momentum operator. So then one can choose a simultaneous eigenvectors. So the N is for the Hamiltonian, and the J and the M so labels the states for the J squared and the JZ. So we have as our simultaneous as commuting what to say as mutually commuting operators. Yes. Okay, so then we can label the states, eigenstates like this. So this is one example. Yes. Yeah. Cartesian symmetry, and we can generate the multiplets. So we have a set of different m, and they have all the same eigenvalues, as you know. Yes. That's one example. So now we look at particular symmetry. So we will consider basically two specific symmetry operations, namely parity. So that's kind of fancy name. So that is basically a space inversion. And then later, we will also consider time reversal symmetry. So this is a little bit tedious. So actually both of these symmetry operations are discrete. So obviously when you have inversion, you just have two operations. Invert. And you have the unit operation. It's identity operations, so you only have two elements. And with the same with the time reversal, basically. So let's start with space inversions. What do we mean by space inversion here? So the inversion operator, call it pi, that, and we define it with respect to the position eigenvector. So when it acted on that, it will change the eigenvalue to minus x. Yes, that's natural. You have minus, so because you invert things. So it's unitary because we don't change the magnitudes. So we take the overlap of the state minus x with itself, where that should be equal to the original state, or the overlap of the original state. So that implies also that this thing is equal to x pi dagger x. So that tells me then that maybe compare these two. That tells me that pi dagger pi is equal to 1. So that means that pi dagger is equal to pi minus 1 if we multiply both equations from the right by pi minus 1, and we get this. So that also means that pi is Hermitian because we get pi to the minus 1 is equal to pi, and that's equal to pi dagger. So we can see this by applying the inversion operator twice. So we get so pi squared is equal to 1, and so that implies that if we make comparison with this, that pi dagger must be equal to pi minus 1. Okay, so that's some basic properties. And we can also show that this imperative operator has eigenvalues equal to plus or minus 1. So we take state alpha, let's say it is an eigenstate inversion operator with eigenvalue alpha, and we apply this version operator again. So that would be then be alpha squared alpha, but this is equal to 1. So then alpha squared is equal to 1, or alpha is equal to plus and minus 1. So you have the eigenvalues of the symmetry inversion operator to be plus and minus 1, which is the even and odd eigenvalues. Okay, so let's have a look at wave function. We look at the state tilde. So we apply this to an arbitrary state psi, and we want to see how the wave function looks like. So since the pi is defined with respect to position eigenvector, so we want to insert a complete set of states in between the pi and the state psi. So that gives me minus s prime but I can just make a change of variable from x prime to minus x, and then get the same integral here. Then should be minus. Yeah, so this is, I guess, okay, so I can just, I can call it y if you like. So you can call it this. What? Y minus y, yes. So goes to minus x prime like this. And the integral does not change because it's still the same range. So if I have a minus, minus like this, but this goes from minus infinity to, so it goes from minus infinity plus infinity. So then it becomes dy. Yes. So if I take the projection to position eigenvectors, that gives me the wave function. Then we see that is equal to psi minus x. So if the psi tilde, if psi is an eigenket of pi, then this is equal to pi psi. So if this is an eigenket of pi, then it must be then plus or minus psi, like that. So we see that the corresponding wave functions will be minus x, and that is plus or minus psi x like this. So the eigenstates is either even or odd. Yes. So the wave functions corresponding to an eigenket of the inversion operator has this property that is either even or odd. So let's go a little bit further. Yeah. So we also want to know how the this inversion operator, um, how it so I want to say that what is the commutation relations of this inversion operator with position operator. So to figure this out, look at the expectation value of the position operator in the tilde state. So we can write it like this. We insert complete set of states. Okay, let me just continue here. So this, of course, just give me x2. So then the whole thing becomes x2 gamma delta. So we integrate one of these variables, let's say x2, then we end up with psi. Why do I have psi here? Ah, yes, that's because the previous result that we have, this is equal to that one. And we have x1 here because of the delta. We have minus x1. Sorry. So if we then change the variable, that becomes minus x1. Sorry. And we realize that these are just 1 if we integrate over x1. So then we get, it's not 1, but position operator. So that becomes like this. Yes. So we say that the expectation value of the position operator in the tilde state is equal to minus the expectation value of the position operator in the original state. So this implies then that dagger x pi is equal to minus x, or the anticommute, which is kind of expected. Yes, this is, after all, the pi is the parity operator, inversion operators. I would expect that it reverses the position operator. Okay, still have 5 minutes here. We can continue. We can also figure out the commutation relation of the momentum operator with respect to the inversion. So we expect that it will be the same as the position operator, but let's check that. Show that. And to show this, we use our translation operator. So we use the fact that the momentum is the generator of translations, this translation operator. And we can show that t dx this is equal to t minus the x pi. Yes. It's quite a straightforward algebra here, but let's go through this properly. So let's look at the effect of applying the left-hand side to some arbitrary state psi. So then it gives me pi t dx, and then we insert the completeness relation. Oh, let me see what I'm doing here. Strange thing. And be just like that. So now I can use the definition of the translation operator so that we just shift dx prime by dx. And then we can use the definition of the inversion operator, so that becomes minus x prime minus dx. So like that. And so let's do the right hand side here, and we want to show that they are the same. So again, we insert complete set of states. So that gives me minus x prime. I know this is quite straightforward, but it's good to little exercise here to see how things work. So now we apply the translation operator. So we will shift to minus the x prime by minus dx. So we see that they are the same. It's the same. So we have this property here. So that means that if we plugged in this t here and here, then we immediately obtain the commutation relations between the momentum and inversion operator. So then we get also the pi and the p anticommutes. Yes. Yeah, so from here, yep, that one. So okay, so let's continue with angular momentum. So for the angular momentum, it actually commutes. So we can see this from the fact that angular momentum is cos p, like that. So since both R and P are anticommute, both R and P anticommute with inversion operator, then then the inversion operator commutes with the angular momentum. So then we, like before, we assume that this is also true in general for J. Where J can be just usual angular momentum or spin. Okay, so maybe it's a good time to stop here and we just continue with the rest of disparity and the time reversal symmetry. So even so although the inversion symmetry seems very simple, it can have some interesting consequences. We'll discuss this later, next time, on Friday, I think. So let me check. Could we have it on Friday or Thursday? Yeah, it's on Friday. Okay, so before we start, maybe we have any questions about this stuff here. Okay, so if there are no questions, then we stop here and say goodbye.
Thanks.
Everybody. Thank you.
Bye. Thanks.
Thank you. Bye-bye.
Bye.